Hello there. We're going to be doing what I like to call a boss fight of Gen Chem thermodynamics problems. This problem, what is the free energy change of the reaction under the following conditions? So we have a whole bunch of concentrations over here at 25 degrees Celsius. And then we're given the reaction, it's the dissociation of acetic acid, and we're given the equilibrium constant for this. Okay, so we're given a whole lot of information and we're asked to find delta G. So we're going to be using two very important equations from thermodynamics in order to answer this. The first one up here allows us to relate delta G standard with KEQ, the equilibrium constant. Now remember, delta G standard is the free energy change under a very precise set of conditions. It's 1 molar of everything, 25 degrees Celsius, and 1 atmosphere of pressure. The second equation allows us to find the delta G under non-standard conditions, specifically concentrations, if we know delta G standard. So, we've got some work to do. First things first, let's take it from the top. Let's find that delta G standard. How can we do that? Well, once again, if you know KEQ and you know the temperature, 25 degrees Celsius, we can find delta G standard using this equation. So, delta G standard is equal to negative R. We're going to use 0.008314 kilojoules per mole Kelvin. It's our gas constant. Our temperature here, we need to do our temperature in Kelvin. So 25 degrees Celsius, add 273 to that. It's 298 K times the natural log of KEQ, which is 1.8 times 10 to the negative fifth. Okay? When we do all of this, we'll end up getting that delta G standard of this reaction is equal to positive 27.1 kilojoules per mole. So, under standard conditions, this reaction, as written, would be decidedly non-spontaneous. But are we under standard conditions? Is it 1 mole of everything? We can see that's not the case. Okay, now that we have delta G standard and we know the concentrations, we can use these concentrations and our standard delta G and relate them to our delta G under these decidedly non-standard concentrations. So let's do that. First, I always like to solve for Q before putting everything in together. It helps keep things more organized. So let's do that. Always write an expression for your reaction quotient Q. Q is equal to products over reactants, so it's the concentration of CH3COO minus that we have at a given time times the concentration of H plus, all divided by the concentration of our reactant CH3COOH. Okay, so I'm going to plug in our values. We've got 2 times 10 to the negative fourth. We've got 1 times 10 to the negative seventh for our H plus. And we've got 18 molar for our concentration of acetic acid, CH3COOH. It's all said and done. This ends up equaling Q equals 1.1 times 10 to the negative 12th. Okay, now that we've got our delta G standard and our reaction quotient Q, we can put them together into this equation and we can solve this problem. Figure out what is the free energy change under the specific set of conditions. So let's do just that. We've got delta G is equal to our delta G standard, which is 27.1 kilojoules per mole, plus R, 0.008314 kilojoules per mole Kelvin, times T, 298 K, times the natural log of our reaction quotient Q, which we figured out was 1.1 times 10 to the negative 12. Okay, so the natural log of 1.1 times 10 to the negative 12th is negative 27.5. We multiply that by the rest of this, And what we end up getting is delta G is equal to 27.1 kilojoules per mole plus, and this ends up being negative 68.2 kilojoules per mole. So just add these two values together and we get our answer. Delta G is equal to negative 41.1 kilojoules per mole. So that is the free energy change under these conditions. Oh. And it's worth pointing out that even though reactants are heavily favored in this reaction, our delta G standard is fairly positive. Our equilibrium constant, we can see 1.8 times 10 to the negative fifth. This means that at equilibrium, we'd have decidedly a lot more of the reactants than the products. That being said, given this particular set of circumstances, where our Q is even smaller than K, you can see that we still ended up with a negative delta G. So this reaction, as written, would spontaneously go forward to make more products until it reached the equilibrium constant K. Thank you very much for your time. Have a great day.